Hi, my name is Samantha Hunsel, and today I'm going to be exploring a group theoretical analysis of cyclic numbers as my senior capstone project. My advisor was Dr. Garth. Thank you so much for helping me explore this topic. It was really interesting, and I'm super excited to share it with you all. So first, we're going to go into a brief introduction, and then we're going to go into two different modes of thought. We're going to look at cycles of decimals and whether they terminate and repeat, and then the group ZM star, where M is a full rep 10 primed, a composite M, and a power of prime. And then we're going to look at the cosets of the group generated by 10 as well to help us explain some of these behaviors. And so if you were like me in school, you may have gotten bored in class and you may have fiddled around with a calculator, which I certainly did. This example is something you may have come across. 142,857 multiplied by 1 is itself, but when I multiply it by 2, I get 285,714. What's interesting about that is that it is just the same digits, 1, 4, 2, 8, and 5, and 7, just in a different order. Actually, if I multiply 142,857 by the numbers 1 through up to 6, I get the same digits as 142,857, just in a different order. So I get 1, 4, 2, 8, 5, and 7, all in just a different order. It's not the only number that does this. In fact, 76,923 does this, and it does this with two different numbers. If I multiply 76,923 by the numbers 1 through 12, half of them will give me the digits of 0, 7, 6, 9, 2, and 3 permuted, but the other half will give me the digits 1, 5, 3, 8, 4, and 6 permuted, which is very intriguing. We will call the numbers like 142,857 and 76,923 cyclic, where they produce permutations of digits like we've seen here. These numbers actually come from the denominators of fractions, and prime denominators are especially interesting when we're considering cyclic numbers. And so I have here just a table of a few prime denominators of 1 over that denominator, and then the numbers that are cycled that are associated with them. And so you may recognize row 1 from our last example. That comes from the fraction 1/13th, and there are only two numbers that come from that, from 1/13th. You can see 1/17th only cycles one really long number, and 37 cycles 12 really small ones. So we have varying lengths of and varying amounts of cycles between determined by the prime denominator. And you may notice we have a 0 in front of a lot of these numbers, and that's just to show that it's included in the permutation of the digit. And so we are actually going to explore more in depth the origin of these numbers. And we're going to start off with just the decimal expansion. We can write a fraction as a base 10 decimal expansion, and actually we can write any real number as a decimal in a base 10 expansion. For example, 1/8 can be 1 over 10 plus 2 over 10 squared plus 5 over 10 cubed, which is 0.125. And we can actually express 1/8 in like a different base, like 60. But for this discussion, we're just going to limit ourselves to base 10 because that is a standard unit for us when we are studying. And so while this theorem gives us that this holds for any real number, we will actually restrict our attention to rational numbers because they both terminate and repeat. And what I mean by terminating is that the decimal ends in a string of zeros. And so we see that the decimal expansion of 17 over 400 does end in a string of zeros, but we just usually truncate those zeros and call it 0.0425. When I say repeating or purely repeating, I mean a decimal expansion that has a repeating block of numbers. And so like the decimals of 1/3, 1/7, and 1/6 all repeat because they do not end in a string of zeros. 1/3 repeats 3, 1/7 repeats 1, 4, 2, 8, 5, 7, and 1/6 repeats 6. But 1/3 and 1/7 has purely repeating decimal expansion because it repeats a specific block of numbers, but 1/6 repeats only 6 and not 1, and so it's just repeating. Repeating is the terminating part, or 1 is the terminating part, and 6 is the repeating part. Now we kind of wonder, are there conditions for this type of behavior? Yes, there are. In fact, there is a theorem that states these conditions. When we look at a fraction a over b, where a and b are relatively prime, we can say some things about the denominator b and determine when a decimal or the decimal expansion of the fraction will terminate and it will repeat. And this theorem says that if the denominator has only factors of 2 or 5, it will terminate, and that's expressed in b equals 2 to the alpha, 5 to the beta. If the denominator has factors of 2 or 5 in addition to another factor, which q is that additional factor, it will have a terminating part and a repeating part. And if the denominator has no factors of 2 or 5 at all, it will purely repeat. And we can see this theorem in action. So here is a table of m and the decimal representation of 1 over m. So m is a denominator. It's just from 2 to 21. And we can see that the numbers in black are the numbers that are terminating. They have factors of 2 or 5 only. So 2, 4, 5, 8, 10, 16, and 20 are factors of 2 or 5 only. 3, however, is a purely repeating decimal, and the red ones are. And so all of the red ones are. And so we see 7, 9, 11, 13, 17, 19, and 21 all are because they have no factors of 2 or 5 at all. And it makes sense that the primes that aren't 2 or 5 will be purely repeating because they're all odd. And so that aren't 2 or 5. And so they don't have a factor of 2 at all. And if they had more than 5, if a factor of 5 that's greater than 5, it also wouldn't be as well. And so we then can say, though, that not all of them are prime. We see that 9 and 21 are not prime and they are purely repeating. But we can also then look at the blue ones, which are just repeating decimals, and they have an additional factor in addition to 2 or 5. So like 6 is 2 and 3, and we see it ends in 1 and repeats 6. And 15 is 3 and 5, and it ends 0 and repeats 6 as well. And so those are the ones that are just repeating. And since the cyclic numbers originate from decimals that repeat digits naturally, we will just concern ourselves with the denominators that repeat. So ones that have factors of 2 or 5 with an additional factor or none at all. And now we're going to move into the group of units modulo m and talk about them a little bit. As a refresher, it is a abelian group under multiplication. It is composed of elements a such that a and m are relatively prime and they have no factors with each other. And this is useful for is that when we observe a subgroup of 10 generated by 10, we can relate it to the fraction 1 over m for z m star. And this is because we're using a decimal system here. I want to make an important distinction. I want to make sure that we know the difference between the order of a group and the order of an element. The order of the group is just the number of elements in the group. So the group of units modulo 10, z star 10, has 4 elements, so the group has order 4. However, when we talk about the order of an element, that is the smallest positive number d, such that a, an element in the group, to d is congruent to 1 mod m. The element 3 in z star 10 has order 4 because 4 is the smallest positive number such that 3 to the 4th is congruent to 1 mod 10. And that is that case. And so the order of the element and the order of group, especially when we're talking about 10 and the group generated by 10, are similar. But more specifically, we will use these two definitions to describe the number of digits that are cycled and therefore describing the permutation length of a decimal expansion. But first, we're going to start by observing z star p for prime p, so it's when m is prime. We know that the order of 10 mod p is p minus 1 due to Fermat's little theorem and Euler's totient function, results of those two things. And this is where we actually find our purely repeating decimals. There are no factors of 2 or 5 for primes not equal to 2 or 5. And so that's where we get our purely cyclic numbers. So if we go back again to looking at 1/13, the 13 and 10 are relatively prime, so we have a purely repeating decimal. It cycles 6 digits since the order of 10 mod 13 is 6. And actually, if we multiply 1/13 by powers of 10 and observe the decimal result, we can see that at 10 to the 6th, which is the order, well, 6 is the order, we see we have the number 76,923, which is one of our cyclic numbers, with, of course, remainders. And you can see the remainders going up there on the right of 10, 9, 12, 3, 4, and 1. Those are actually only half of the 13ths, right? We're still missing ones like 2 13ths, 5 13ths, 6 13ths, etc. And we're also missing another number. Remember, 1/13 is associated with 2 different cycles. Well, if we actually look at 2 13ths and we do the same thing, multiply it by powers of 10 up to 10 to the 6th, we see we get the other cyclic number, 153,846, and the other half of the remainders for of 13ths. And this is actually because of our congruences. Like 10 is congruent to 10 to the 7th mod 13ths, and so that's also the reason why 10 to the 6th is congruent to 1 mod 13 as well. And so we have the following congruences that make that happen. But now let's look at a more special case of primes that gives us more interesting results. They're called full repten primes. So first, we'll just define what a primitive root, or otherwise known as a generator, is. And that's an element G that generates every element of the group of which it belongs. So if I take powers of G, I will get every element in the group. And so for a full repten prime, a prime where the decimal period of 1 over p is p to the 1 minus digits long, these two are actually connected. And so we can first see that 1/7 is a full, or 7 is a full repten prime, because we see 1/7 is a full repten prime because 6 digits are repeated, which is 1, 4, 2, 8, 5, and 7, right? But we actually have a theorem that says more specifically, if p is a prime and 10 is a primitive root of p, then the decimal for the fraction 1 over p has period of length p minus 1. So 10 being a generator for z star p specifically means we will have a purely repeating decimal with period length p minus 1. And so going back to 1/7 in mod 7, we know that 6 is the order. And so if we look at the subset generated by 10 of z star 7, we see that it is the group z star 7. There will only be one cyclic number associated with it because it generates the entire group. And so full repten primes will only have one cyclic number associated with them, and we will see the entire numbers there. Unfortunately, there's not much else known about these primes. In fact, they're only 6 below 50, but they do produce interesting results with cycles. But now we're going to go ahead and lay some groundwork and move towards talking about z star m for a composite m. To do that, we're going to need to look at the cosets of the group generated by 10. And if we recall that the cosets are subsets denoted AH for A and G, the elements of the cosets of the group generated by 10 in z star m are exactly the remainders when performing the division algorithm on 1 over m. And so that's how they're related to the decimals. And then the quotients of the division algorithm are the digits that cycle when we perform the division algorithm on 1 over m. And multiplying the elements of these cosets by the cyclic number associated with the group gives us our cycled number digits. And so if we're looking at z star 13, we see that there are only 2 cosets, which makes sense. When we perform the division algorithm on 1/13 and 2/13, the cosets are, or the remainders are the cosets 1 times 10, the group generated by 10, and 2 times the group generated by 10. So you can go ahead and do that for yourself. Divide 1 by 13 and 2 by 13 and look at the remainders, and those are those respective cosets. When we continue the division algorithm and look at the quotients, we do get the following expansion. And you can see our 2 numbers that are cycled are 76923 and 153846 there in our numerators. And so just to show you that if we take 076923 multiplied by the elements of the cosets, and I highlighted those in red there, we get our 2 different cycles of numbers, and they're the remainders, which makes sense with our last example of looking at the remainders of 13ths in this case. So now we're going to just go into z star m for composite m, and something that will help us will be the external direct product of the groups, and it's more specifically a theorem. So if we suppose that S and T are relatively prime and that we look at Z star ST, we can say that it is isomorphic to the external direct product of Z star S and Z star T. And that mapping of the isomorphism is just taking the element mod ST and mapping it to the same element mod S and the same element mod T. And so a way we can calculate then the order of 10 to find permutation length of decimals is by this theorem. We can find the order of the element and the direct product of a finite number of finite groups by looking at the least common multiple of the orders of the components of the elements. And so we can help use this to break down large M when we're looking at Z star M. And we can more easily take the order of 10 in it. So let's go ahead and look at an example. So suppose we want to find the permutation length of 1 over 3,157. It's fairly large. So we see that we can turn this into an isomorphism of the external direct product of Z star 7, Z star 11, and Z star 41. And 7, 11, and 41 are all relatively prime, so it works out. So then we can map 10 to that external direct product and we get the element 3, 10, and 10. And then we can find that order in the external direct product and we see that that order is 30. And so since the mapping is an isomorphism, we can then say that the order of 10 in Z star 3,157 is 30 as well. And so then the period of 1 over 3,157 is also 30, and that will cycle 30 digits. And so that is very helpful, like I said, for very large M, and when we're looking at composites. And our last case to consider now is when we look at Z star M for a power of a prime, P to the N. And we actually have a theorem modified from Introduction to Number Theory where the motivation is similar, except that this is not for primitive roots. And this is just for the order of 10 because 10 is not always a primitive root. If it was, it'd be a full rep 10 prime. So this theorem says that if the order of 10 mod P to the N and the is D, but the order of 10 mod P to the N plus 1 is not D, we can then find the order of 10 mod P to the K by multiplying it by D and times P to the K minus N. It's what the key fact of this is finding the time where 10 mod P to the N and 10 mod P to the N plus 1 are different. And that is actually relatively difficult. There's actually only a few numbers that do that. There are only actually a few numbers where 10 mod P is equal to 10 mod P squared. And those numbers are 3,487. And then one that's over 3 million large, and you can look that up for yourself. But it's actually quite rare, so this theorem works a lot of the time. And so let's go ahead and look at an example. Suppose we want to find the order of 10 in Z star 343 to find the period of 1 over 343. So we have the isomorphism property there. 343 is the power of 7 to the third. And so now we can calculate its order. First, we'll look at the order of 10 mod 7, which is 6, and the order of 10 mod 49 is 42. They are different. So following the theorem, we can find the order of Z star 343 to be 294. And so 1 over 343 has permutation length of 394, which is a very long number of digits to cycle through. And so now we're going to conclude our topic with a large example, just kind of covering all of the properties that we have looked at so far. And that example is going to be the fraction of 1 over 81. And we're going to see what cyclic numbers are associated with it and what we can tell about their permutation lengths. So we have the factors of 81 is 3 to the 4th. It's a purely repeating decimal. There are no factors of 2 or 5, and it is a power of a prime, you may notice. And so by our isomorphic property, we know that Z star 81 is isomorphic to Z star 3 to the 4th. And so we can use our theorem and find that 10 in Z star 81 has order 9, which is the permutation length of our decimal expansion. There will be 6 cosets generated by the group generated by 10, and those are as follows. And those cosets are the remainders of the fractions 1 over 81, 2 over 81, etc., all the way up to 8 over 81. And so those are the groups of remainders. We can then write the 1 over 81 as a decimal expansion that will repeat. Remember, it does have permutation like 9, and so we see that there, 0, 0, 1, 2, 3, 4, 5, 6, 7, and 9 are the ones that will repeat. And we have draw our bar over it. And so then our cyclic number is 0, 1, 2, 3, 4, 5, 6, 7, 9. And that's the reason I chose this fraction specifically. It's a fun result. So if we multiply that cyclic number by the elements within each coset, we can see the 6 different number cycles because there are 6 cosets. And those are here. At first glance, at the different colors, you may be like, oh, the digits are the same, but there is a digit missing in each one of these of the numbers 0 through 9. And so each of the digits cycled are different. And so we have the number multiplied by each coset's elements of each coset, and we can get the different cycles of numbers. And so we have fully dissected that cyclic number of 12,345,679. And as a concluding mark, we see that while cyclic numbers may seem elementary, it actually took a lot of theory to explain them. In fact, we aren't sure if there are infinitely many cyclic numbers. Emil Artin actually proposed a conjecture that said that the proportion of full rep 10 primes is his special constant C, which is around 37%. So it was saying that the proportion of all full rep 10 primes is about 30, of all the primes, there are about 37% that are full reptend. Actually, this is only true if the Riemann hypothesis is true, which is the most popular unsolved problem in mathematics. And basically, the Riemann hypothesis implies that there would be infinitely many primes. And so if there are infinitely many primes, 37% of infinitely many would also be infinitely many, so we would be able to say that there are infinitely many rep 10 primes if the Riemann hypothesis was true. Unfortunately, it's not, so we are only stuck wondering for now. So thank you so much for letting me take you through my research. I really encourage you to explore more on this topic or talk to me, read my paper. It's really interesting. So thank you for listening.